Hi there, welcome back. In this class we continue our discussion about the estimation of the probability of default of our counterparties when we deal with low default portfolios. That is to say, when we don't have enough information from historical data about the number of defaults for the different types of counterparties we may be interested in. Now, in this class, we go a little bit deeper into the Bayesian modeling of the probability of default. We will see that the idea is that once we have assumed some specific behavior for the number of defaults over time, and the typical assumption is to have binomially distributed defaults, then we put a prior distribution on the probability of default, and then we try to obtain an estimate of the PD for the single counterparty in the case of a low default portfolio. So the starting point is always the same. For the moment, we assume that defaults are independent and that they can be modeled using Bernoulli trials so that the number of defaults is a binomial distribution. So here we are. This is our binomial distribution telling us what is the probability of observing k defaults in our portfolio. Our goal is to estimate small p, that is to say the probability of default of each single counterparty. What we want to do is to use Bayesian statistics, that is to say to use our a priori information for the actual computation of these small p. The idea is to assume that our small p follows a given distribution. This distribution is what is called the prior distribution in Bayesian statistics. This prior distribution represents our beliefs on the behavior of small p, and typically these beliefs can be the results of experts' judgments, that is to say, recommendations that we can obtain from economists, financial experts, and so on. What we are going to do has some very strong similarity with what we did when dealing with mixture models. Do you remember? In mixture models we had different counterparties and we were assuming their defaults to be independent conditionally on some common factors. Then we were modeling the common factors using specific distributions. In the case of one common factor, we have seen, for example, the beta mixing, in which the distribution of the common factor is a beta distribution, and we have obtained the so-called beta binomial model. Okay, in this specific situation, we are doing something similar. We have that number of defaults of our counterparties naturally depend on the probability of default of every single counterparty. Remember, we are assuming independent defaults. What we are doing now is to put a distribution on the small p, the probability of default of each single counterparty. Depending on this distribution, together with the assumption of a binomial number of defaults, we will get different posterior distributions that will be our starting point for the estimation of p hat, that is to say our estimates of the probability of default for our low default portfolio. This similarity is actually more practical than philosophical, because from an epistemological point of view there are differences, but this is not a course on the philosophy of science, so we just deal with the practical implications. Let's start by assuming that our prior distribution on the parameter small p, that remember is the probability of default, is a beta distribution. We already know that if we combine a beta distribution with a binomial distribution, that for us is the distribution governing the number of defaults, what we obtain is the so-called beta binomial distribution, for which we can compute all the quantities we are interested in. Our best estimate for the probability of default, what we call p hat, is in this situation in the beta binomial model represented by the posterior mean, that is to say the ratio of alpha plus k and alpha plus beta plus n. Remember, alpha and beta are the parameters of the beta distribution we are using as a prior, k is the number of default, and n is the total number of companies we are considering. On the course platform, you can find the derivation of this quantity. We have already seen that the beta distribution, the distribution we are now using as a prior, is a rather flexible distribution. On the unit interval 0, 1, we have seen that we can generate very different behaviors choosing the parameters alpha and beta. We can have a symmetric distribution, we can have a skewed distribution, we can also generate a uniform distribution. Obviously, we may want to use other distributions different from the beta ones, and actually we can do that. The simplest distribution you may think of is the uniform distribution. Now, just allow me to be a little bit pedantic, because from a Bayesian point of view, assuming a uniform prior is not an irrelevant choice, is not a non-informative prior, that is to say a prior that essentially reads from the data, you're actually assuming that all the possible values of p have the same probability. So when you listen to people speaking about the uniform distribution as the distribution you use when you don't have information about something, actually it's wrong. You are imposing the same probability for all the values. We can obtain the uniform distribution on the interval 0, 1 as a special type of beta when alpha is equal to beta is equal to 1. In that case, our estimator for the probability of default simplifies to k plus 1 divided by n plus 2. Notice that when k is equal to 0, that is to say when we have observed no default so far, then this estimator is exactly the same estimator we have considered last time in the first class. When dealing with recovery rates and beta regression, you remember in the first part of the course, we have seen that when we have to express a beta of parameters alpha and beta, we don't have necessarily to define these parameters, but we can obtain these parameters from other quantities like the mean and the variance. This is typically what happens. So we don't ask experts to provide us values for beta and alpha, but we ask for the average value of the PD they expect or the variability, and then we revert in order to obtain alpha and beta. If you don't remember how, please go back in the course and check. There are situations in which our economists, our financial experts, may have an idea about the behavior of our probability of default on the basis of a theoretical model or on the basis of industrial benchmarks. Very often they may have an idea about an upper bound, a maximum, and a lower bound, a minimum, and also about what may happen very roughly in between, and typically this can be a mode value, so a value which is more frequent. Okay, this information can be easily embedded into another type of prior, which is the triangular distribution, a very simple distribution that can be seen as the sum of two uniforms. Nevertheless, this is just another possible type of distribution, another possible type of prior. We may think of an infinity of distributions, and you can imagine the results will change accordingly. Very often, if the distribution we are using as a prior distribution is not conjugate, which is a property of distributions in the Bayesian framework, we may need numerical methods in order to obtain our p hat, our estimate of the probability of default. Until now, we have assumed defaults to be independent, so that their number can be seen as a binomial random variable generated by n independent Bernoulli trials. Now, what happens if we drop the assumption of independence? The first consequence is that we are no longer dealing with Bernoulli trials because we don't have the same probability for all the counterparties. We enter in the field of Poisson trials, and this means that the number of defaults is no longer following a binomial distribution, but something else. A very nice model is discussed in a paper by Tasche 2013. I'm posting this paper on the course platform, and I'm also asking you to read this paper because it's really one of the best papers in order to deal with the advanced modeling of the probability of default for low default portfolios. In this paper, the author makes the simplifying assumption of correlated defaults, so no longer independent defaults, but where the correlation depends on a one-factor Gaussian copula, which is a standard assumption in the internal rating-based class. The number of defaults in the paper by Tasche follows what the authors calls a correlated binomial that you can see on your screen. You can see that this is not a simple object, and obviously this object becomes even more cumbersome when we assume that the quantity P, our probability of default, follows a given prior distribution. Nevertheless, what is important to notice here is that the correlation between the different defaults follows a one-factor Gaussian copula model with correlation parameter rho. Once we elicit a prior distribution for the probability of default, we can obtain an estimate of this PD as the mean of the posterior distribution, as the posterior mean. Naturally, the quantity will depend on the prior distribution. In the case of a uniform prior on the 0-1 interval, the expression is what you see on your screen. As you can see, this expression needs to be computed numerically, as we cannot obtain no closed form solution. Okay, for the moment we are done. I thank you for your attention and see you next time. Goodbye.